Hello everyone, welcome to our weekly meeting on Red Hat OpenShift Commons. So what is Commons is where users, partners, contributors, and customers, we meet to collaborate, to contribute, to knowledge sharing, really anything around OpenShift. We meet every Wednesday at 12 p.m. Eastern Time and 9 a.m. Pacific Time. We always use the same link. And we are also looking for speakers. So proposals are now open. So feel free to submit your talk on the blue link. And all our sessions are being recorded. Always you can find it under the same link. And here with me, well, I'm Valentina. Of course, you probably already know me. But here I have two amazing speakers who will be talking about generating Kubernetes network policies at build time with ACS. I have Boaz from Red Hat with me and Adi from IBM. So all the floor is yours.
Thank you, Valentina. Hi, everyone. Thanks for listening and watching this recording. Let me go ahead and share the slide deck. Okay, so today, as Valentina said, we're going to be talking about the problem that, as an industry, we have with Kubernetes network policies and solutions that we can use today to address that problem. And specifically, we're going to focus on a solution that is implemented in ACS, which is a collaboration with the IBM research team. And Adi is here to tell you some of the secret sauce that they have been using to reach these amazing results. So we're going to cover the problem and tell you about how ACS has already handled this and helped customers in runtime. Then move on to how we can improve and move the solution to the left, address it in build time. This is the main output of the NP Guard. We'll include a number of demos, and then we'll dive into the NP Guard magic. So there's a lot to cover. I'm probably going to be speaking quickly, and Valentina and Adi, you can tag me if you feel I'm running out of time and I need to go faster. Let me know. So Kubernetes was designed to be very, very simple in the networking sense that all communication is allowed. Every pod can talk to every pod. And pretty soon as people really started using Kubernetes, the community realized that that's not going to fly. And so enter Kubernetes network policy, which was introduced in 2017. And that is a kind of a firewall capability to restrict pod communication. And we'll talk a lot about these restrictions. The decision was that it would be implemented outside of Kubernetes itself by the plugin. So it's the responsibility of the network plugin to support the specification. Of course, there are plugins that most of them do that, and some of them do more than that. And they support a richer language than the Kubernetes network policy. However, we're going to focus on the language as it is within Kubernetes. So the model that was introduced is pod-centric. And the restrictions that we can apply are, first of all, the focus is on a namespace. The whole conversation is on the pod in a particular namespace. And in terms of ingress or egress, we can specify 4 different ways, 4 different restrictions for other pods to communicate with my pod. 1, I can restrict a pod specifically, no matter where it is. I don't care about the namespace. 2, I can restrict to or allow to an entire namespace, all the pods in that namespace. 3, specific pods in a specific namespace. And 4, is the capability to specify external communication restrictions using an IP range. You can do this for ingress, you can do this for egress. The specification is pod-centric. It's all about me as a pod. Who do I want to talk to, and who do I allow to talk to me? When you're thinking about this in OpenShift space, you also have to consider one of the out of the box, the default behavior of OpenShift is to implement a router, the OpenShift in the OpenShift ingress namespace. And that's the ingress controller, which routes all of the application layer external traffic to your pod. So this is a special pod that you have to consider if you want to restrict communication. You need to be aware that this pod is going to, you need to probably allow that pod to provide you information. The specification allows you to specify port ranges and protocols. It only supports TCP, UDP, and SCTP. So network policy, as I said, is a namespace resource. The way that it works is the namespace selects a pod, and then there are two types of policies. You can have ingress-only policies or egress policies only. In the same resource manifest, you can have both. What is really peculiar about the network policy is that they literally flip the switch. If I have even one network policy that selects my pod, then the mode switches from allow all to deny all except whatever is allowed in network policies. This is done per pod, per policy type, which means ingress type is one thing, egress type is another. Now, there are some complexities with the way that network policy is defined today. It works in a many-to-many relationship, which means that I can have one network policy select multiple pods because maybe I want to apply a certain behavior to many pods at once. But also, one pod can be selected by multiple network policies. So in order to understand what's going on with my pod, I have to analyze all the network policies in this namespace that select my pod. Now, because of this behavior, the network policies are additive. Every network policy can add more and more permissions. There are really no conflicts. You simply allow more connections into or out of your pod. In terms of YAML, what this looks like, let's start to get the taste. Let's look at this cart service pod. This is a network policy of type egress, which selects the cart service by label. And basically it says, I'm allowing communication on TCP port 6379 to Redis cart. This is the egress policy of one of the egress policies for cart service. On the other hand, let's look at Redis cart. In order for communication to be allowed, both sides need to allow it. Whether one of the sides doesn't have a network policy at all, or then everything is out. But if it does have a network policy, it needs to specifically allow the other side to communicate with it. So in this case, this network policy selects Redis cart. It's an ingress type policy, and it has ingress rules that's saying, I'm allowing port 6369 on TCP from cart service. Already you can start to get a feel for some of the complexity in the YAML. This is a simplified YAML. It might not even be accurate space-wise or dash-wise. So if you try it at home, let me know if there's a mistake. But it's really gets complicated as a human being when you're starting to work with these. There are a number of things going on here. We said that you have two different types of policies, but as we saw, you also have ingress and egress rules. What happens if I place an ingress rule in an egress type policy? Well, it's going to be ignored. There are 4 different kind of selectors, as I mentioned. IP block is a beast of its own with IP connections. It's not always clear what happens because the IP address from external, it will probably get modified by the networking components in front of it. And we are only able to specify IP addresses as pods, so that's going to limit. Inside the specification, there are from and to tags. What happens if that's missing? The default behavior when things are missing is quite tricky. And most importantly, there's really no way to know what are the effective rules that govern your pod. You have to look at all the policies in the pod's namespace that apply to the pod. More than that, you can have a resource, a policy resource that lives somewhere, but it specifies your namespace. So you may not necessarily see that resource in your namespace when you're looking for resources. So it really gets tricky, and it's very easy to get it wrong without tooling. But beyond all of that, this was technology. You know what the real problem is? Is people. Because as the way, and we hear this from customers all the time, that the way things work today is that Kubernetes network policies really fall between the chairs. The app devs, I mean, they just want their app to work. They don't want to handle network policies or that stuff. And they don't care about that too much, and it's not part of their development lifecycle, right? So, I mean, I'm developing YAML. At what point do I get to develop network policies? And we'll talk more about that. The Kubernetes admin has the knowledge, has the tools, but he doesn't necessarily know who to go to. Should I go to my SRE, to my app dev, or is it the security team that's supposed to govern these? Well, the security team doesn't necessarily know what the application needs are. And in many cases, they don't understand what's going on in Kubernetes at all. You go to the network security team, I mean, this team is typically out of the loop altogether. So with that is a problem we have to address. And of course, as the SRE says, automate or die. Everything needs to be able to be done automatically. And that's part of what we're trying to achieve here with this implementation. So if it's so difficult, why bother? Like hardly anyone is doing it, so maybe that's okay. So with pod isolation, you can reduce these really dangerous risks to your application running in Kubernetes. We see these risks all the time, except we don't hear a lot about the attacks in Kubernetes. It doesn't mean that they don't happen, and it doesn't mean that they will not happen. Maybe we got lucky. But consider data leakage and exfiltration. If somebody is able to infiltrate to your pod and that pod can talk anywhere, they can send the data anywhere they want. Of course, unauthorized access to your your data from that pod, be able to move laterally from one pod to another. And if you have no protection, of course, you're more exposed to denial of service attacks. So there are many good reasons why we need to protect and isolate our pods as much as we can. So how does ACS already help do this today? ACS has a number of tools. They are accessible in Runtime, which is based on ACS observing the communication patterns of your application, of your workload. And you can go to the network graph, and in the network graph, you can visualize active flows, which means these are connections where we see traffic. You can also visualize inactive flows, which means this is traffic that your network policies permit, but nobody's using them. So it's probably a good idea to set up network policies and restrict those unused connections. At a pod level, we can also show you which network policies are active for that pod. That's, again, information that is really hard to figure out. And we can also alert or enforce if pods are missing network policies altogether. The next level is the network baseline model. As I said, we observe the network traffic, and users can control which of those connections that they see listed are part of what they view as healthy. We record for a certain time. So if you have new connection that is fine, just was missed in the recording, you manually can add it. And then you can also work in a way, once you're happy with a baseline, that you create an alert. If anything goes outside of that model, you will get a violation alert. You can, in fact, even enforce that violation. Next, there is a policy simulation mode. So given that baseline, you can use ACS to generate and export a network policy that cements the model that we're seeing. Now, our policy in runtime that we generate is only ingress. We don't provide the egress for the reason that we feel that we don't have enough information in that baseline, and we don't want to break the application. So then you can use that and bring it back into your GitOps, use that as a base for your network policy, upload it, and you can, in fact, you can also play with that from within ACS itself and visualize the impact. So let's move into the first demo. We're going to use an online boutique demo that...
There is a question.
Oh,
yeah.
Go for it.
Ram, go ahead. Ram, I don't know, maybe it was a mistake.
Okay.
Yeah, continue.
So let me get out of this for a second. And so I want to share a couple of things. I think it's going to be easier to share my entire screen, and I'll just drag stuff into the screen. If there was a question, go for it. So this is what I'm going to use. This is a demo that was adapted from Google demo, and it in a way that it works with OpenShift completely. So I've already pre-deployed that. And this is my OpenShift cluster view with these deployments. If you go to networking and the routes, you will see the front end running on this page. And this is the application. So it's a working application, a really nice demo to play with. I can come in here, I can browse, I can buy stuff. Oh, that's an error. Of course, the demo gods are not with us right now, as you would have it. But the nice thing is that normally this application works and generates traffic. And let's see if I can move to US dollar. I don't know if that was the problem at all. Probably not. Okay. But this is the idea. So now I go into ACS. And this is the network graph view. I'm focused on this shop demo. And what I did now is I clicked the front end. So what I can see here, I can see these active connections. I can see my ingress and my egress connections. I can see a lot of information, additional information here on the side. And I can see that there are no network policies. So what I can do is I can come in here. Right now I selected the whole namespace, and I'm going to generate a network policy. Okay, no need to be selected because demo gods. I probably just have a network policy in there. So let me try to clean that up real quick. Actually, it's easier to do it from here. So actually, you know what? I'm probably going to skip that for now. When I load the network policy, since I have it in my folder, let me try to share that.
I really love this graph and the visualization. It's very interesting. So thank you for the live demo. I know that sometimes it's not always perfect. So thank you for doing this.
That's right. This is the demo gods working with us. So this is the way that the network policy is. Let me see if that's the right one. That was created by StackRox, and you can see that we have. Well, actually, you know what? I'm gonna come back to that. This is the wrong network policy, and it's not gonna work right now. But the way that you will see is that I could generate here. Probably, you know what? Last attempt is I'll just try to refresh, because this window has been stale for a while, and maybe it's just an access issue. And yeah, maybe that was the issue. It's been stale, so I guess that is the problem. Do I have more luck on this window? Aha. Okay. Yep, because the network policy here was already applied, and I didn't clean it. All right. Let's go back to our presentation. I think I can probably do that right now and clean it up. Aha. Okay, maybe we're back in business. Okay, so I don't know if you noticed, but the little icons here changed from something that was protected to something that is not. And I can come in here. I have my baseline, and I'm going to generate a network policy. It's covering all these 12 deployments. I'm going to generate and simulate. This is the network policy.
Nice.
And now I can download it. As you can see, it was downloaded into the same folder. So you know what you do is you rehearse, and then you get stung by your own rehearsal. And here, I'm going to apply the network policy that I just generated. And once I refresh, indeed, I can see now that these workloads are secured. They have an incoming network policy, and I can continue to explore using the graph. I can also look at the network policies. I can select them one by one. If I just select the workload, or if I select the entire namespace, I'm going to get all the network policies, and I can browse and go into the one that I want and edit it or inspect it. So let's clean up.
This is great. Thank you. So Ram had a question. If he's saying, if he was wondering what is the source for creating a baseline for network flows, is dependent on what CNIs expose, or does ACS uses eBPF or some mechanism to capture the traffic?
Okay, that's a deep question. We do rely on eBPF. Yeah. So we are looking at system calls at the eBPF layer, and based on that, we figure out what is going on. Okay, let's go back to our story. How do we shift this left? Doing this in runtime is great, but it might be too late. Or in other words, what if we could do this sooner? And of course, Rockscuttle is already active in the pipeline. There's image scan, image check, deployment check. So what about Rockscuttle netpull? There is this new command in ACS in build time that's called Rockscuttle netpull. What can you do with it? So imagine that we could automatically generate network policies for you in build time. Wouldn't that be nice? Here on the right is the AI view of the machinery that it would require to achieve that task. Well, it's actually much easier. We're going to look at several commands, and the first one is Rockscuttle netpoll generate. And the way this command works is it looks at a folder with fully qualified YAMLs, and it generates a network policy for you. There are certain artifacts that are valuable here. We create default deny. It's a tight ingress and egress per flow. We only allow DNS if we detect it, and this is important to prevent DNS data exfiltration. And this works very well when the YAML follows best practices. So in other words, if you're a developer and you're just doing what you're supposed to do, and Adi will talk more about what that means in detail, this should work. So let's go back here and let's see if we're in the right environment. This is how the application looks like. I simply have here all the YAML resources. I also probably have some connectivity files that I created before, so we'll see if we need to escape any one of them. Let's just make it easier, and we can use the generate. So I'm going to use this command. And sorry, because I don't have the right, because actually this was the right command. So now we created a file, a network policy. Again, if we try to look at that using code, let's just bring that into the view. In this folder, I just created this file, a network policy. So we can see that this was generated. It includes ingress rules, ingress and egress type. If you study this deep, you can see all of the services that you saw in the demo. So we have the cart service, checkout service, network, and we have default deny. So that's nice, but it's complex, right? So what is the next step for a developer or a DevOps team that is trying to use this? So the next step is, how can I visualize what just happened? And in order to visualize, Rockscuttle looks at same folder where you have all your qualified YAMLs and network policies that were generated either by this tool or elsewhere. And in the output, we can provide output using text, JSON, or DOT and CSV format. So let's go back and look what that looks like. And in this case, I will do a connectivity map. And in the output, already I can see the same, I see the output that will be provided in a file, but I can see here the format is like a from, so the card service, sorry, some initial setup for colors, but then I can see the connections. So for example, a checkout service, which is a deployment, is allowed to make a connection to the card service using TCP 7070. So it's a little hard to see DOT. I could do this in text, but instead I'd rather show you this in DOT format right out of my VS Code. So this is the graph that reflects the network policy that I just generated automatically. Look at how clean this looks. By the way, you can play around with different formats if you like them. And you can already start to analyze the network policy that was generated. Now, it is generated automatically, but doesn't mean it's perfect. So it's a starting point. It's a very good starting point, but you have to do your research and make sure that it's appropriate. And Adi will talk about some of the caveats that might be present at this stage. You can also do, if this is a little too complex, you can also focus on one. Let's do it. Just run this command. So if I do, I'm going to override it by adding the -- remove. So I just created another file that is, in this case, focused on one particular workload. So in this case, I created this checkout graph. And if I can remove some of the others, I don't need this, just make some more space. Then again, well, okay. So here we can see this graph. It's just a connectivity graph, but this time it's focused on the checkout service. So I can really just zoom in and figure out what was generated. And now it's much easier to see, have I allowed all the connections that I need to from ingress and egress perspective? Like I said, there's a lot to cover and we're starting to run out of time, so I need to move a little faster. The next and the last demo that I want to run for Rockscuttle is, it solves a really hard problem as you develop these network policies. And think about, you're working in Git and you're submitting PRs. How do you know what changed between one version to another? So in this case, we have the Rockscuttle connectivity diff, and this command, let's do this command takes two folders, and as output, it shows you what has changed. Let's just do it here. And we'll just even use the text output format for now, because we see that in this case, there is a single change that was caught. And it says, look, in this, in what is the different type is something has changed. It could be added or removed. And it's saying that your front end can now talk to your ad service. Previously, you only had this port. Now you have these ports. And so out of the sea of changes, because if you just looked at the network policy, it would be quite impossible to catch that. But Rockscuttle Netpool actually understands the change, whether it came from a resource YAML or your network policy. So that's another important tool in your arsenal. So moving on to how this magic is done, and I'll just give you kind of the high level, and I'll let Adi talk about the details. But just before I move to this, again, just to kind of wrap up on what you can do with Rock Scuttle is work in build time, and you can make that part of your DevOps chain, whether it's used by developers, which, by the way, this Rock Scuttle command does not require a live connection into ACS Central. So anyone can use it. It acts like a local tool. It's just standalone. As you can see, I just ran Rock Scuttle and it works. So developers can use it. They can just download it to their laptop, use it. DevOps team can use it. And as we mature with this, is we expect people to implement that in their pipes, so that network policies can be automatically generated, and then somebody sends a PR to approve it before the network policy goes live.
Hey,
So how question?
Yeah, I just have a quick comment. So one of the things, like if you look in real world, right, like most of the time these manifests gets dynamically like generated, right? For example, customized, folks might be using customized. They don't like really physically exist. You're either using Helm or customized, right? To create these things. So
Right.
one of the things that I noticed, like when I was playing with this, was like I wish the CLI allowed I wish there was a way to pipe basically like a customize, like do a dry run and then pipe it into the command to actually create the connectivity files and whatnot. But for now, like what I had to do was I had to like drop it into like a temp directory and then use that as an input. So just as a feedback, like it would be nice to be able to pipe the output from like a customized or Helm into the rockctl.
That's great feedback. Thank you very much. Yeah, this is kind of early stage because as we, unfortunately, most of our customers and the state of the industry is people don't really use network policies as much as they should. So I'm really glad that you're starting to work with this tool. So how do we do this? We run this static analysis on the resources, and first thing is we look for the service manifests. So as destinations, we're going to try to understand from all these YAML resources, which one of these resources acts as a destination that someone will try to talk to. Then we scan all the different types of resource manifests, and they're listed here on the right, to try to look for connection hints. And these hints, again, is just if you follow best practices, we will find these hints, because you're not supposed to have this in hard code. You're supposed to have it just like it is in these YAMLs as kind of a name value. It could be in a config map, but it will have some kind of this format, which we heuristically look for, and usually we find. And then we match the egress network addresses to these destinations that we already addressed in order to understand what are the required connections, who is trying to talk to whom. And we can derive all the ingress and egress relationships based on that, and create a network policy that cements that relationship and creates a tight binding too. So we also limit egress to only what is required. In addition, we include some organizational governance. So there are some built-in rules that you might need to tweak. And right now we have one, which is a built-in rule to allow DNS for egress. Why? Because if you look at the YAML, you will not see that anyone is trying to call to DNS. It's built into the code. So we treat DNS specifically, but you can imagine in the future that we'll have additional rules. And then again, this is the generated sample. I'm going to skip it for the benefit of time, but if you study these slides later, you can carefully look at the example that I was using, the card service, and how it talks to ingress and egress based on what's allowed. And this particular one example where there's no egress allowed, so it is blocked.
Boaz, you have 2 minutes left, so we have enough time for Adi to do the presentation.
So I have
perfect.
So I have 2 minutes to waste now.
Great. Now, Adi, it's all yours then. Thank you.
So now let's move over to some of the detail that Adi will take us through.
Yeah, thank you. So I will start where you showed this slide already.
Let me actually just switch out and kind of go into a presentation mode.
Yeah.
Oh, wrong one. Sorry, just keep going.
Yeah, thanks. So I'm from the NPGAR team and developing this analysis, static analysis and generation of network policies from IBM Research. And yeah, back to this slide. We assume that our input is those YAMLs or manifests of your application, Kubernetes service, the Kubernetes workloads, and maybe config maps. And for the output, we generate a recommended network policies. We try to identify the required connections for the application to work. And based on that, to generate the network policies automatically. This works well only when those YAMLs are following the best practices that I'm going to specify now in the next slide. Yeah. So first, we assume, as we discussed, that the YAMLs are not in templates like in Helm. And then we assume that the application specifies the network addresses for each microservice in the YAMLs and not hard-coded in the application code. So this is best practice. It's very common. And we assume it could appear in containers env, the environment variables that are available for the container, or through config maps, or through command line arguments. And I'll show you examples for this in a few slides. So this is very common as best practice, and it has to be used this way so this analysis can work, and so we can identify the required connections for the application. And we also assume that the network addresses are matching the common URL patterns and using the Kubernetes service FQDN names, such as the service name itself, or the service name followed by the namespace, or the service name followed by the namespace and by the cluster.local service cluster local suffix, and could be attached with a port number and prefixed with HTTP or HTTPS as the URL. So these are the examples for the patterns that we're looking for while analyzing and looking for network addresses. Let's go to the next slide. Yeah, so based on that, we want to identify the required connectivity between the application's microservices. So for each service, we first check the possible network addresses that could be used for this service. Then we identify all the workload resources that are using those configured network addresses with the which are pointing to any of the identified network addresses that we already saved earlier. And if we identify such reference of a network address with the pattern that I specified earlier, we have a potential required connection for the application. So we save it in our list of required connections. And we have a source workload, the target workload, and the port information, if possible, if available from the address. And let's see examples, a few simple examples. These are the YAMLs. This is a deployment YAML, and you can see in the bottom part, you have the env of the container part, and it encodes here those variables with the values that are of the format of the service address that I specified earlier. In this case, and in the next slide, we see what are the connections we identify. So this is the front-end deployment, and we can see that based on these addresses, we identify it should be communicating with the Redis service, the workload behind it, over TCP 6379. So this is one example of how we identify. Another example is in config map variation of this. In this case, the variables are actually defined within the config map resource, not directly in the deployment YAML. And we do this referencing and checking whether this is encoding a service address that we identify. In this case, in the next slide, we see that the identified connection here is from checkout service to the shipping service over this port, based on this value of the network address from the config map. And in the next example, another variation, it could be from the command arguments, command line arguments given for the container image. In this case, it's the currency service being used as the service address with port 7000, and this is the identified connection. What we do with those list of required connections that we identify, this is how we build the network policies. So in the next slide, how do we build those network policies? We go over this list of required connections, and for each workload, we specify the ingress rules and the egress rules based on these connections. So where the workload is a target, it should be specified as an ingress connection, allowing this from the source workload in the connection with the relevant ports, and in the other direction for the egress rules as well. And a few more details here. For the egress part, we also need to allow DNS access. If the workload has to communicate in the egress direction, it also needs access to the DNS. So for this, we create another rule to open the DNS port over UDP into the entire cluster. And in the ingress part, we also take a look at the service type. If it's not a cluster IP service, if it's a node port or a load balancer service, we assume it needs to be exposed externally. And thus, we add another rule to open it externally for any source. And if it's pointed by an ingress resource or by a route resource, we assume it should be accessible by the ingress controller or the router of the cluster. So for this, we add a rule to open it ingress from any source in the cluster. Let's go to the next slide. Yes, we also add a default deny network policy. Yes, there was a question.
Yeah, I was wondering if you're using like service binding operator, is that something that can be used as a source to identify what are the services that it's talking to? Like, are you familiar with service binding? It's okay if we. I was just wondering. Service binding is basically an operator used to connect services together.
No, I'm not familiar with this operator, so you can check that. You can look at that.
I'll take that offline.
Thanks. Yeah, so basically we just use this static analysis that I mentioned over the YAML manifest. And we also add here a default deny network policy for each namespace that we identify. So that this is useful when you add new workloads. First, this is protecting your workload in the namespace. And then you have to add those policies to specifically open what is required. So this is basically the part of the generation of network policies. And now I'll talk a little bit about roadmap and future features. So back to the visualization part. Let's take a look at this example. You might wonder, is this sufficient for me to review the connectivity? Where is the part of the DNS port that I mentioned earlier? How do I see that it's accessible here? I don't see it here, the UDP port. So you might wonder, yeah, I need to go to the YAMLs and take a look there. Where are these rules? What is actually open? So why it's not in the graph? Because this DNS pod is not in the YAML manifest of the application. And this connectivity graph is only showing you those nodes of the identified workload from your input manifest. And for this, we added a new feature called exposure analysis for this connectivity map command, a new flag. to show you what your policies are exposing potentially to other entities in the cluster that are not present in your input manifest. So in this example here, these UDP ports are reflected, and you can see now that you've opened them to the entire cluster over this UDP port. For example, in the payments namespace, the gateway deployment, it does need egress access to other services. So the policy does open UDP egress rule to the entire cluster. And this is reflected in this new exposure analysis graph. It can basically provide you hints or help you validate that you're not overexposing by network policies, or if you do overexpose, what you could possibly limit and restrict connectivity. So I think this is an important feature for the visualization of the connectivity, even though these are not actual connections permitted between two workloads, concurrent workloads. There are potential workloads in the cluster that might be willing to accept such connectivity from the configured workload, as this rule, one of the network policies, opens this connection. So in this case, let's go to the next slide. How could you?
Quick question on this slide, Adi. So the square brackets, they represent namespaces.
Right.
So in this example, and this is really the best practice, is analyze all of the code that you have together. So obviously there's an application here that is using multiple namespaces. So as an organization, you should analyze all of this together and provide the complete picture to our analysis tools.
Right. Yeah. So, for example, here you could be limiting the connectivity that I showed you, where you were exposing your connectivity on UDP to the entire cluster. Maybe you know where your DNS pod is configured. It depends on the environment. It could be Kube system namespace or OpenShift DNS namespace, depending on the Kubernetes cluster that you're using. So in this example, I can edit the rule of those YAML of the network policy that we generated earlier to be more tight. In this example, I add this rule to namespace selector to restrict it only to the OpenShift DNS, because this rule is meant to allow only the DNS traffic. And then it gives you the opportunity to have tighter policies and even improve it better. So if in the next slide, I show the graph generated after adding this rule. And now you can see that actually the exposure is only to the OpenShift DNS namespace for these pods and not to the entire cluster. The exposure to the entire cluster is remained only for the workloads in the ingress direction for the ingress controller. For this, you could also restrict even more if you know where your ingress controller is configured, in which namespace, and on which labels. You could also edit this rule and restrict it even more. So yeah, this is what is planned as a future feature for this connectivity map command.
I'm so excited about this feature. It really brings this feature into like full, I think, full usability, and really you can start to you can start it now, but with that analysis you can drive security in build time. With like there will be no more excuses not to do that. By the way, we mentioned here port 53 and 53. So people working on OpenShift, be aware that this is the default, and you can change that default in the command line for Rockscuttle when you're generating these artifacts. So I think that brings us to the end of this session.
That's great. Thank you. Yeah.
Thank you for the questions.
Yeah. Any other questions? And yeah, it seems the service binding operator and found the webs. Yeah, the information seems yeah is deprecated. So just wanted to clarify this for everyone who is watching. Yeah, any other but amazing presentation. I love network policies. I don't know, I just love it. But I do felt like that we needed a better way to visualize it because it's very difficult to know, and to debug when there is an issue. So that what you both show us today are like really nice ways of doing this and also track changes. So thank you so much. Any questions? Any other questions for Adi and Boaz?
Were there any questions in the chat that we missed?
No, we are all good.
All right.
So do you have any recommended resource for who could be interested in learning more? Something that they can, follow up, after watching this video?
So absolutely, just it's a good question. There are a couple of places that you want to be watching. There's a StackRox community, and in the slide deck that I'll share later, I'll add the link to that community. And the other thing is that there is a button on ACS. There's a little red button at the right that says feedback. And this is for our customers. And we are, as the product management team, receives these requests directly. So this is your gate, your opportunity to share your feedback with us, whether something you are missing or whether there's something that you like. Please use this feedback button and let us know what we can do better.
That is great. Fantastic. Okay, well, with that, thank you so much. I will see you everyone next Wednesday. And now I will stop the recording. Thank you.